Hello everyone. In this video, we are going to talk about vibration isolation. Now, this is a brief introduction, and this topic could be just a course of its own if you really want to talk about it. So here we just want to talk a little bit about the idea of transmissibility and three different methods of vibration isolations. We introduced them. The pictures are taken from these websites, so the credit, not this one, but or this one, basically these guys, this one and these two and these. Okay, they are coming from different websites, so I just put them there. So, what is vibration isolation in the first place? It's basically decoupling the source of vibration from the structure that you don't want to shake as much and move as much. Okay. Like, for instance, earthquake and a building, or I don't know, the unbalanced masses or the vibrations from motors, and then the equipment that are cutting something very sensitive, right? So high precision machinery or anything like that. Specific cars that you have seen, they have amazing vibration isolations. You see they go over all sorts of bumps, and then you see they put these water cups on their hood, and you see that the water cup does not spill, right? So those have very accurate and most of the time active or semi-active vibration isolations that can give you that perfect ride, so you don't even feel that you're driving over all these bumps. So we have to use springs, dampers, and so on, but the fact that whether these springs and dampers, especially most of the time dampers, are basically passive, which means their values are constant and pre-selected, or we can change their values during the operation. That is, as we'll see, is the difference between passive and semi-active isolation, and then whether we bring in an extra actuator to kind of cancels the vibration forces, that will be active isolation. So first thing is, if you remember, in one of my previous videos, I talked about force vibrations of single DOF systems with the motion of the base, right? So that was this video here, with support displacement. And I showed you that basically we focus on this relative motion, and then we find the transfer function, and then we can find now the absolute motion of the object, the ratio of that over the motion of the base, and the motion of the base was a harmonic function like y equal magnitude y sine omega t. So we found this ratio, which is magnitude of x over y, and you see it's a function of frequency, kc, and m. And this ratio here, that is the target magnitude of vibration to the source magnitude of vibration, here this function is what we call transmissibility. Okay, which this formula again is for a single DOF system. So you can write it in terms of ck omega m, or you can write it in terms of the ratio of omega over omega n, where omega n is the square root k over m, and damping ratio, which is, or damping factor, which if you remember, zeta was c over 2 square root km. Okay, so this is that function. Now, if we plot this function again here, so I plotted it again for different zeta values, okay, you can see that this is the transmissibility plot that you will get. So magnitude t versus omega over omega n, and these are for different zetas, as you can see. If we zoom into the region around the ratio of square root 2, so there is here, this is square root 2. If we zoom around that region, you see these different zetas, okay? The order of them on the left side of this and the order of them on the right side of this is different. For instance, here, the curve that was on the top of all of them, the blue curve, which was basically the smallest zeta. Now, if you look at it, when you go to the right side, it's underneath all of them. or the one that was below all of them on the left side, which is 0.7. Now you see when you go to the right side, now it is above them. So the order of this magnitude would reverse. Okay, for different zetas, that order would reverse based on the ratio of omega over omega n, and this ratio is square root 2, where the transition happens. And of course, around 1 is where you have these resonance, correct? That is your resonance here. Now you know that a ratio of 1 is only for case that zeta is 0. When zeta is not 0, you shift a little bit to the left. You do it at omega r, if you remember, which I showed you how to calculate it. Please go back and look at my video. So what does this one say? It says that, hey, when this ratio is below square root 3, if you want to get less transmissibility, and less transmissibility means smaller x. For the same y, it means smaller x. So it's always desired to bring down this transmissibility, right? We want to have smaller magnitude of output compared to the input. So it says if you're on the left side of it, if you want to get better or reduce transmissibility, basically, you need to increase the damping. And you see that here, the top one is 0.01, the bottom one is 0.7, and the bottom one has a smaller one. So on this side, make zeta go up to get t to go down. That's what you need here on the left side. On the right side, on the other hand, if you want to get smaller numbers, you see, you have to go to smaller zeta. So here, if t wants to go down, your zeta should also go down. So if you take advantage of this and you have a system that you can modify your damping factor based on the ratio of omega over omega n, you can switch between these curves. So on the left side, you are on the purple curve. On the right side, you jump to the blue curve or something, okay? And that will help you keep this transmissibility around 1 or below 1 for most of these frequencies, okay? So that, of course, needs a system that you can actively modify your damping value. If you can change this damping coefficient, so this damper is not constant, it's basically a variable damper, which you can see in pictures like that. That is the essence of what we call a semi-active vibration isolation, and we're going to look at that. But this is one thing that we want to know. So now let's go and talk about these different categories of vibration isolation. First one is passive isolation. So all here you do is to use springs and dampers and try to minimize that transmissibility as much as possible. The good thing is they are inexpensive, they are reliable, they don't need any power, and they are relatively good at high frequencies. All you need is to pick a good K and a good C and follow that instruction that I said as much as possible. So what kind of thing would you use for springs? Of course, use coils or different types of springs. For dampers, typically you use different types of plastics or anything that can absorb vibrations. For instance, in engines, you can use these guys, which are, you can see here in this picture, they are engine mounts, okay? And you see they are mostly kind of like rubber. And also you can use these anti-vibration pads that are made from neoprene, okay? So these guys, and again, they are really great in damping out vibrations and turning the vibration energy into basically heat or something. Because if you remember, in one of my previous videos about rolling resistance, please look at it. It should be under statics playlist, I guess. I talked that if you look at the stress versus strain or force versus displacement diagram for rubber, you see that when it goes up like this, and when it comes back, it comes like this. Okay, so inside this, there is this kind of loop, right? And we called it hysteresis. Hopefully I didn't have a typo. So this is a loss of energy. Here, the energy you spend to deform it is not the same energy that you get back. So this portion, this energy inside this cycle, which is the area inside it multiplied by the volume. That whole energy is what is converted to heat or sound or something, especially heat, and you will never recover that. So they are really good at killing out the mechanical energy of the system due to vibration and damping out the vibrations. Okay, you just need to pick proper C's and K. The problem is they are really good for the high frequency range. Okay, in the low frequency range, regardless of what C or what K you pick for the system, there is resonance. Okay, so you have to deal with this. So in the low frequency region, your resonance can still happen. So you have to make sure that if it's a machinery, you have to make sure that the operating frequency is way above the natural frequency, so you don't deal with resonance. But if you're riding a car, the frequency of the bumps on the road, they are not under your control. You don't have control over the operating frequency. So you might get some big bumps in the road, okay, and big vibrations up and down the ride, we call it. Okay, so these are really good in high frequency range, and picking better C's and better K's will make this region better. But again, nothing is under your control. So the good thing about them is they are inexpensive and they are not requiring any power. Okay. The other problem they have is their settling time is typically long. So when the vibration happens in these systems, if you look at, for instance, X of t, then you see that when this thing starts and then it goes like this, it takes quite a bit some time before the magnitude of vibration is, let's say, for instance, plus or minus 1 or 2% around 0. And this time here, which is called the settling time, I explained that in vibration controls, and this is like 4 over zeta omega n or 5 over zeta omega n, depending on what percentage do you use, 2% or 5%. This can be quite a bit long, so you'll feel the vibrations for some time before it literally settles down to 0 or very small numbers. So for that reason, in cars, in machineries that need better vibration isolations, they try to go with active or semi-active isolations. How? So in an active isolation, which is like the most, I would say, complicated, the most sophisticated one, here you have sensors to sense the vibration of the system. So by sensing those vibrations, because remember, the solution here is definitely of the same frequency as y. So if this floor is moving with y of t, and that y of t, as I said, is like y sine omega t, the main frequency for x is also going to be omega t. So if I have a way to fill this x of t, I should be able to sense that omega. I should be able to get the frequency of my signal as well as the magnitude of it, correct? So I can get the magnitude of it, I can get the frequency of it. If there is a phase, I can isolate all of that, right? And based on those, I should be able to infer my input magnitude and frequency. Good. So now what? If I infer my input magnitude and frequency, then what I can do is I can add actuators to the system that will cancel the force coming from the floor. Because remember, the force from the floor, if you remember, it was C times y minus x, both of them dot, and then K times y minus x. So these are the forces that are applied to the mass. And if I know my x and y as a function of time and I can calculate these terms, ideally I'm trying to apply some kind of force from the actuator equal and opposite direction that they would cancel those forces and my mass does not really feel the vibrations. Okay, so what I need is an actuator, a hydraulic actuator, or any other type of actuator that can apply a force in the opposite direction to the forces from the floor to the mass and cancel those. So with some simple extra control force, I can force my system solution X to converge to zero. Then we say we fully isolated the vibration and we did not really allow this X to constantly fill this harmonic excitation. Okay, so although the bump under the car is just continuously oscillating, but your X gets some small thing and then very fast it downs to zero, so you literally don't feel anything. So here the equation of motion will be mx double dot plus cx dot plus kx equals the control force plus the force from the base, which you can also write it as negative my double dot. Now the control force, as you can see, tries to, as I said, create an equal and opposite force for the floor. So these two would cancel each other, and also it can add basically a PD control here. Okay, and a PD control, when combined with this, your equation of motion will be something like mx double dot plus x dot times basically kd plus c, and then plus x times kp plus k. This goes to zero, and of course this is a homogeneous solution, so x will be something like x0 times e to the negative lambda t, where lambdas are roots of this, and by picking appropriate kp and kd, I can pick my lambda. Okay, so you see, in order to calculate this force, in order to calculate this control force, I need to have sensors. Sensors should sense for me x and x dot of the mass, and from the x double dot of this, I should be inferred y double dot, or from x and x dot, I should be again able to infer omega and y. So I can form this y double dot, which, remember, it is negative y omega squared sine omega t. So if I form these forces in my hydraulic or any other type of actuator, most of the time hydraulic for heavy masses, then ideally I can do much better job. So here is an example of transmissibility for an active and a passive vibration isolation. You see the red curve is passive and the blue curve is active. And you see that while the passive still shows resonance here and large magnitudes, the passive will never go, let's say, anywhere above 0.5, while the active one, if you look at it, this magnitude is about 2 or 3. Okay, so it is amplifying, really, right? The magnitude of vibrations for the system is 2 or 3 times bigger than the source, while here is never more than half of it. And if you look at it, so this system at low frequency has no resonance. Okay, this system does. That's very good thing, that the active system works perfectly in low and high frequencies. And you see that this system will much faster go to small numbers than this system does. And then the steady state error here is very small, here is quite a bit bigger. Now you might say, why you never get it to perfectly zero? Could you get it to perfectly zero? Well, you might not, because getting the values of c, k, omega, and cap y and exactly identifying them with zero error is impossible. So you can get only good approximations of omega and y, but never perfect. And many times this omega and y do change along the time. They are not constant. So in this simple case, we say y of t is y sine omega t, which means omega is fixed, y is fixed. The matter of fact is, if you look at the road profile, it's never a perfect sine wave. Okay, so you might have something here, then constant, then something else. So your magnitudes and frequencies do change. And for a system in real time to estimate them very accurately, that is almost very, very hard. But if you do a relatively good job, you can get those forces to almost cancel each other. So because the system is using sensors and actuators, of course, it needs constant power consumption. Of course, it is more expensive. And of course, it gives you better performance in dynamic environments, as I said, where omega and y are variable. Because in a passive system, you pick the C and K based on what you think the omega is going to be. So if omega changes, whatever design that you had for C and K will now be not super useful, because you design it for one omega, now you have another omega, so the system will not do a great job. And as we said, in low frequencies, these systems will not have resonance mostly. Okay, so where would you use them? Use them in high precision, for instance, electron microscopes or precision manufacturing tools. They really need to cancel the vibrations to the best that they can, so the end of the tool will not oscillate when cutting the material, and you can get very, very tight tolerances, let's say. Okay, so this is active vibration cancellation, and then there is semi-active. In semi-active, you don't have an actuator to cancel the forces, but you can adjust the values of damping or stiffness in real time. Now, because there is no actuator, you don't need as much power and it's not as expensive. So it's a compromise between simplicity of passive and performance of active. Here, what you can do is, as I said, you change the damping value or the spring value, most of the time just the damping, and I'll tell you why, to basically move or switch between these curves, basically, as I said. Okay, so you can switch between these curves by changing K or C, and as I said, the best one is CY, because if you look, when you change C, you're only changing damping factor, but if you change K, guess what? You change both omega n and zeta. So you are changing two things now, the natural frequency and the damping factor, which is not a good idea. It's always good to only change one of them, not the other one, and keep one of them under control. So most of the time it's the damper that is variable, and it's easier to change the damper value than to change the spring value, because this spring, okay, in order to change the stiffness of that, it's not necessarily easy. If you know, for a tension spring, let's say, the K, if you know from machine design, or if you don't, go and watch my video under playlist machine design where I talked about the spring constant is equal to, so it was G, the modulus of the shear modulus, which depends on material, times basically D to the 4. This is the wire diameter, over 8 D cubed. This D is the diameter of the coil, and times N, and N is the number of basically active coils. Okay, or you can write it in terms of pitch if you want as well. But clearly, changing the number of active coils, or the wire diameter, or the diameter of the coil itself, or the material, is much, much harder than changing here the viscosity of the fluid. Because remember, these viscous dampers, they have basically something moving inside a fluid like oil or something, and changing the viscosity of that is possible through one mechanism is called magnetorheological dampers. What is that? These are the kind of oils for which the viscosity can be changed by applying a magnetic field. Okay, so here you have MR fluid piston. Inside of them, if you look, the fluid here, basically the viscosity of the fluid depends on the magnetic field. If you apply different magnetic fields, the viscosity, or the C constant, which depends on the viscosity, does actually change as a function of magnetic field. Now, how does it do it? Well, inside this fluid, inside this oil, there are magnetic particles here, okay? So it's not just a pure fluid. Inside of this, there is magnetic particles plus oil. And so when you apply a stronger magnetic field, that causes these particles to basically align and form a kind of structure. And it's not now easy to move the oil with these structures of magnetic particles form inside of it. So when the magnetic field B goes up, the viscosity mu, or in other words, C, will also go up. Okay, so by changing the strength of the magnetic field, you can change, as I said, the viscosity or the damping coefficient here. And when you change the damping, you change zeta. And when you change zeta, as I said, you switch between these curves. Okay, so this is called a semi-active suspension or semi-active vibration isolation. Now, it just switches between the curves. It does not fully cancel the vibration force, so it can never fully basically isolate the vibrations, but it can reduce the magnitude of it. And of course, it's a little bit cheaper too. So if I want to compare these three major methods for vibration isolation, briefly just summarize it. In passive vibration, you only rely on simple passive mechanical elements. In active one, you have hydraulic systems and sensors, actuators to cancel the force. Here, you just adjust the damping or stiffness, mostly damping values. The passive system does not require any energy and the system is not complex, while active does require a power supply and it is quite a bit complex because of all sensors, actuators, and so on, and controllers. Semi-active is lower than active and higher than passive, so it needs variable dampers and simple controls. Okay, and of course it does not need as much energy because all you need is to change the magnetic field here. Now, passive ones are good mostly for high frequencies. At low frequencies, they are not great at getting rid of those resonances. And when the disturbance is large, okay, so that Y is big, they do not do a great job. I just found that I had a typo here, so I fixed it. The active ones are good at a wide range of frequencies and disturbances. And semi-active ones, they are good for small to moderate disturbances. When the disturbance is very large, then they cannot do a great job. And again, here, this should be mostly low frequencies or large disturbances. The cost, of course, is active is the most expensive one. Semi-active is moderate and passive is very low. Of course, passive does not use any power. Active uses the max power, and semi-active is the exactly the midpoint. The same thing goes for the maintenance: low maintenance passive, high maintenance for active, smaller maintenance for semi-active, and different examples. For simple equipment isolation, simple industrial machinery, we use passive vibrations. For tables that we use for sensitive instruments in expensive cars, basically in, as you saw, electron microscopes and so on, we use active ones. And in some of the cars and some of the buildings, we use semi-active. So hopefully this video was useful to you. You learned some basic things about transmissibility and different ways for vibration isolation. Thank you so much. I'll see you in the next video.